Okay, I think we can start. It's 4:15 p.m., so it's good time for start. Our next Warsaw Quantum Computing Group meetup. It's episode 57, and we organize it today on Sunday because it's a special day. It's a World Quantum Day. And we have pleasure to host a great speaker, Mateusz Ostaszewski, who will tell us about quantum architecture search. So we've agreed with Mateusz that you can, if you have any questions, you can raise your hand and we can interrupt during the lecture, but hopefully there will be also time for some Q&A session after the lecture. A few words about World Quantum Day, and by the way, have a happy World Quantum Day today. It's an interesting initiative. I think the organization started a few years ago. The day is April 14 because 4.14 is an approximation of the Planck's constant. You can find the details about this project initiative on the website of the World Quantum Day. We would like to thank our strategic partners. I know that some of them are with us today, like Sonovero R&D, for example. There are also some honorary partners who support us in advertising the event. Yeah, so I will later tell about some links to follow and join after the lecture. But now I will give a voice to Mateusz, and if you are ready, the floor is yours, and I will just change the slides.
Hello, my name is Mateusz Ostaszewski, and I'm currently a postdoc at Warsaw University of Technology. And today I will briefly introduce the topic of quantum architecture search. So I would like to start with this brief sketch of hybrid quantum classical algorithms. So they're based on the interaction of classical computer with quantum device. So on classical computer, we construct quantum program, which is on the top of the diagram. Then we execute this quantum program on our quantum device. After the computation, we perform the readout, and the output of the readout will be the input to the classical computer, based on which hopefully we will improve our quantum program. And when I'm talking about quantum program, I mean the evolution operation of quantum state. So this is this operator U. It has some mathematical formalism, but on this presentation, let's say that this our quantum program will be presented by this quantum circuit. This is this object in the purple frame, and as we can see, we have horizontal wires. They denote the indices of qubits, and on each qubit there are some gates. We have in this circuit, we have two types of gates, single qubit gates and two qubit gates. The single qubit gates, those in the rectangles with RZ, RX, RY, RZ, those are rotation gates. So the index XYZ, this is the axis of the rotation, and we have also they are parameterized, so the theta are the angles of the rotation. And we have, in this particular case, we have two qubit gates controlled NOT gates. And those gates are important for us because they allow to entangle those qubits. So they provide those quantum effects. Without two qubit gates, then we will not have any special effect and benefits from this circuit. And yeah, and let's assume that this is our alphabet of the gates. And then after this evolution, so we start with this initial state 0. We perform execute our quantum program. So in the resulting state, we have new state psi. And after that, we perform measurement. And from the measurement, we estimate our, let's say, objective. So as you can see, our objective from the measurement, it depends on this, our resulting quantum state, but also it depends on some operator H. And this operator also, as operator U, has some mathematical properties. I think the maybe worth to mention, this operator H has this property that its eigenvalues are real numbers. But what I think it's also nice to mention that the operator H encodes some, let's say, practical problem. Practical means, I mean that it in this operator H we can encode, for example, some electronic structure of the molecule, or it can encode some I don't know, combinatorial optimization problem like traveling salesman problem. So then this whole program, the aim of this program is find the quantum state, so essentially the vector, which corresponds to the eigenvector of this operator H, corresponding to minimal eigenvalue, right? So essentially our external problem, this quantum chemistry problem or combinatorial optimization problem, in the end comes down to finding the minimal eigenvalue of our operator H. Okay, so assuming that we have, for example, fixed circuit, fixed architecture, we have those continuous parameters, the angles. So when we want to find the solve this problem, so find this minimal eigenvalue of our operator. So classical computer using some optimization techniques like, I don't know, gradient descent, Corbel optimization, whatever, prepare some set of angles. We apply them on our quantum computer. After the evolution, we have new state. We perform the readout, and based on the readout, we estimate our objective, right? This is important that the objective is estimated. So, this is not exact result, but this is the input to the classical computer based on which it will propose some new set of parameters. And this is this scheme, presents the general variational quantum algorithms, like the class of those hybrid quantum classical algorithms. And I would like to go back a little bit to this picture with quantum circuit. I hope it will somehow help to understand the next slides. So as you can see here, we have additionally those red lines. They split the circuit into the layers. Thanks to those layers, we are able compute the depth of the circuit, which is important. I will explain it later why. So in each layer, as you can see on different qubits, we have different gates, but we cannot have two gates on one qubit within one layer, right? So thanks to this, we can imagine that the circuit is like this 2D grid where we have those vertical indices of qubits and horizontal and vertical layers. So then we can say that we want to put some gate in the position ij, right? Some exemplary circuit. So, for example, on the left we have UCCSD architecture. This is physically motivated architecture, which usually constitutes a lot of gates, which is not desired property. On the other hand, we have on the right hand side we have hardware efficient architecture, and as you can see, it is very simple structure. So we have those blocks in the brackets with 2 layers of rotation gates and the full ladder of 2-qubit gates. Hardware efficient. This is also something that it's worth to mention in this quantum architecture search domain, because each quantum device, each quantum computer has its specific quantum connectivity topology. And here we have some exemplary topologies from IBM different devices. So also here we have like additional constraints in our architecture search. That means that we are not able to connect 2 qubits, arbitrary 2 qubits with those 2-qubit gates. Okay, so when we are trying to design our architecture, we have to deal with this expressibility and trainability trade-off. Expressibility means that our circuit has to be able to generate our state that we are looking for. So in the case that our task is to find the minimal eigenvector of given operator, our circuit has to be able to generate that state. So it has to be expressive enough to generate the state. But on the other hand, it has to be we have to be able to train the circuits, right? So we have the architecture, which in theory, like UCCSD ansatz, is able to generate this state, but because of some additional constraint, it is hard to train this architecture. And for example, impact on the trainability, for example, has measurement noise, because as I mentioned, the objective is estimated. So not all optimization algorithms work well with this noisy landscape, in this noisy objective. Then we have physical noise, where the amount of noise is contained in the grade, and it has impact on their optimization landscape, and it grows with respect to number of qubits or with respect to depth. And for example, 2-qubit gates usually are much noisier than single qubit gates. So then we have this trade-off, because we want 2-qubit gates to have entanglement, but then it constitutes more noise in our circuit. And of course, there is bar and plateau phenomenon. So gradient vanishes exponentially with the number of qubits or the depth of the circuit. So here we have from the article from Nature Communication the exemplary figure, which shows how landscape behaves under the deeper circuits with more qubits. So that's also why, like for example, UCCSD, as I mentioned, usually they are very expressive, but unfortunately there's a huge problem to train them, because they are usually very, very deep. So of course, in the end, those are the constraints that we have to deal with, proposing the architecture, like designing this variational quantum algorithm. And that's why, I guess, people trying to deal with it try to adapt methods from neural architecture search, from deep learning. So in general, in neural architecture search, we have search space, which defines the pool of the allowed, operations, some connections between those operations. We have some search algorithm, which give us the rule how to sample the candidates from our operator pool. And in the end, we need the evaluation strategy, right? So, okay, we sampled the candidates, but we have to evaluate them, how they are good in our task. And this is like this inner loop between the search strategy and this evaluation. So I guess this is straightforward, that the blocks in the neural networks correspond to the gates, the quantum circuits. The weights of the neural network easily you can map into the parameters of quantum circuit, the angles. So exemplary methods in quantum architecture search. There are sampling-based learning algorithms, differential quantum architecture search, reinforcement learning-based algorithm, and evolutionary algorithms. In this presentation, I will try to cover first three methods, but also there is a lot of manuscripts about evolutionary algorithms in this domain. Okay, so sampling-based quantum architecture search. So at the beginning, we have to set up the pool of operations. So we have this math called G. This denotes like the alphabet of our basic gate. So based on our previous slides, you can assume that it, for example, is composed out of 5 gates, like those 3 rotations, controlled NOT gate, and for example, identity, right? So the empty slot. And here we have like all allowed circuits in the end, because we have product. Usually, as I understand, the people somehow this operator pool is handcrafted. So like this is not really all the possible circuits, but there are some, you know, designs, like some rules of thumb, how to what kind of sub-circuits will be present in this. Usually there are, you know, those blocks with as in hardware efficient, where you have like the rotations. After that, this some ladder of 2-qubit gates. But overall, the maximal number of configuration is exponential with respect to number of qubits and the depth. So this is the power of our gate set and to the power of n and l. And for a large number of qubits and large number of layers, this parameter space is hard to optimize. And therefore, people utilize this parameter sharing strategy. And I will show an example in the next slide of this sub-circuit with which share the parameters. So okay, so we have this operator pool of the operators, and next step is the optimization step. So we have like some capital T iterations. In each iteration, we sample the circuit and we optimize it, right? So this U with index small t, this is some peaked sampled circuit, and we optimize the angles, and we perform it capital T times this operation, the sampling with optimization. And exactly here, when we are optimizing for given circuit the parameters, and for example, our circuit have this inside this structure as in this red brackets, where we have this layer of rotation gates. Then, as we can see, this structure is similar. So this structure is similar between first and second circuit, but it is different to this third circuit, where on this second position we have RY, not RZ gate, right? So all circuits with this particular structure with RY, Z, YY, when we optimize, we draw one of these circuits and we optimize those gates. So all these parameters will be shared within our pool of operations, right? So therefore, you know, performing those capital T iterations, in the end, at some level, we are optimizing all the parameters inside of our optimization pool. And next, we sample, after this T steps, we sample K architectures, rank them, yeah, because they are optimized already, rank them, and we pick the best one, which has the best energy. And we retrain this best architecture, because maybe this architecture was never directly optimized in this optimization procedure. Maybe it has only, kind of a little bit tuned parameters because of this parameter sharing. So we do the full retrain to have, full performance of given architecture. And this is like the brief introduction of this quantum architecture search. Of course, there are some variation about this method, like for example, you can run in parallel multiple, search algorithms when we have copies of our operator pool in separate threads, independent threads. You're performing the same algorithm, and in the end, again, we have couple of candidates, and we can vote which is best, right? Next algorithm, which I guess builds upon the previous one, is the differentiable quantum architecture search. It relaxes the discrete architecture search to continuous space. So again, we have this gate set, right? So at each position in our 2D structure, we have to decide, right, in this IJ position, which gate do we want to put. And to this decision, we model this decision with probability distribution. In this case, with softmax distribution. So for each position in this 2D grid, ij, we have real parameters alpha. Alpha is the vector which in each position corresponds to different gate, right? So in our previous case, it will be 5-dimensional vector because we had like 5 gates, right? So our objective right now has 2 continuous parameters, the angles as previously, and those continuous parameters alpha. And the full circle looks like this. So again, classical optimizer, classical computer, which updates our parameters alpha. After that, we have new probability distribution. We sample from this probability distribution some batch of the circuits, but of course those are only architecture. So we have this internal loop where we optimize the angles based on how good are those the performance of those sampled circuits. This is the feedback to the quantum computer to update the parameters alpha, right? So again, the search algorithm, how will we sample? This is the decision of classical computer. And one of the recent papers, Quantum Darts, I think it was published on last year ICML conference. They proposed like few tricks in this quantum differentiable quantum architecture search. They changed the softmax distribution to Gumbel distribution, but also they proposed 2 versions of the algorithm, like this macro and micro search. Macro search, this is essentially what I described right now. So the search space is large because we assume like full number of qubits, full depth, and the gates are the basic units are the single gates. So this is what I mentioned previously. But also there is this micro search which works on smaller space. And the aim of this micro search is to find those smaller sub-circuits, like on this example, when we see that there are essentially the same operators. They work on different qubits, but the structure is very similar. And this micro search is the hope that this whole method will scale, really, right? Because of course all the methods. The results are presented on very small molecules, for example, which we are able to simulate. But because of this micro search, which divides the problem into smaller subcircuits, smaller instances, there is hope that from those smaller subcircuits, it will be able to construct those bigger and larger circuits. But as I understand in this paper, the main results are presented on macro search. There is only one section with the micro search results into 2 domains, but like the main comparison with the other algorithms was based on the macro search. So I guess it is more accurate. So that's why they presented those results. And last method where I have a little bit experience is the reinforcement learning based search methods. So in reinforcement learning, we have an agent which performs some action, so interacts with environment by performing some action. And based on this performed action, the environment change the state, and agent receives the reward. Like formal description of this whole domain can call like Markov decision process. It has some important components like state space. So this is the analogy to our search space, right? In those search algorithms. So in our case, the state space will be the quantum circuits. The action space are the gates. so agent append new gate. In our scenarios, we don't have this dimension of depth because we are always appending gate at the end of the circuit, right? So you have to decide, only agents to decide which gate and on which qubit, right? And then we have like the probability, state transition probability and the intermediate reward. But in our case, those are deterministic except the reward, yes? Yeah. Yes. In our case, of course, you can imagine some other scenarios, but we are working on this. Reward is based on the energy, so this is not obvious, of course, that it will be deterministic, but state transition is deterministic. Okay, so in our reinforcement learning setup, aim is to train the policy so that essentially the policy is the probability distribution that for given state S, we will pick some action, some gate. And to evaluate this policy, the helpful concept is the discounted sum of the rewards, right? So we have this g tau. Tau is the trajectory, right? So we assume that agent performs some sequence of actions. So after each action, it receives the rewards, and the sum of these rewards, or discounted sum of these rewards, is the aim of the agent to maximize this return, right? Gamma is the discount factor. If gamma is equal to 0, then for agent only, the next reward is the most important thing. If the gamma is closer to or gamma is equal to 1, then the last reward is as important for the agent as next reward, right? And to be honest, we steer this gamma because, as I mentioned, we want to have short circuits. So we want to encourage agent, to produce as short trajectory as possible, right? Of course, we are not setting it to 0 because then it will be greedy. We want the agent to have this, long horizon to find the finally the expressible circuit. But steering this gamma, we encourage it to produce as short as possible. So finally, to evaluate our policy, we use this return, and to evaluate the policy, we use concept of expected return. So this is like only the expectation value over the trajectories generated from our policy. In the end, our objective is to find the policy that maximizes this expected return. So, and here we have the brief sketch of this loop, where we have the state, MDP state, right? Which I mentioned, this will be a circuit agent which append new gate. So we have new state. Based on this new MDP states, which is circuit, we have the internal loop where we optimize the angles, and based on those optimized angles, we compute the reward, which is the feedback for the reinforcement learning agent. And going a little bit more into the details, for example, how do we encode the quantum circuit to be an input of our neural network? So we code it into the 3D binary tensor, when one dimension is the number of qubits, one dimension is the depth, the maximal depth, and the third dimension is the encoding the type of the gate, like using one-hot vectors, whatever. Yes, and right now, two slides about the comparison. So we compared our reinforcement learning quantum architecture search method with this quantum architecture search, the second citation. This is this method is sample-based learning method. They in their paper, they had the experiments, this energy in this last row. This is from their paper on the noisy environment, on the noisy setup with molecule think 4-qubit hydrogen. So as we can see, their energy is not passing the chemical accuracy, because chemical accuracy is slightly above 10 to the minus 3, and they have 16 gates. In our case, the best energy, so this is like this first row, unfortunately it has 32 gates, but if we will take, we'll try to find the among all the circuits that agent proposed, which are below chemical accuracy, and we will pick the shortest circuit, we are able to pass chemical accuracy with 10 gates, right? So we have better results in this setup. And also we have in our paper comparison with quantum darts, this differentiable quantum architecture search. They propose in their paper 3 molecules, one in 2 versions, 4-qubit and 6-qubit. And as we can see on the left, this is our method. Most of the energies is better than theirs. Also, usually we find shorter circuits, shallower, and also our algorithm utilize less gates. But of course, this is not perfect. At some scenarios, they are going better. Of course, this is still, a developing domain. And going to conclusions, what are the challenges? I think the ultimate goal is to, find the solution that will work really on the large scale. All those methods, in the end, they are, there are some theoretical analysis that it will hopefully, like this microsearch, will work in large scale, but there is no hard evidence for that. This is of course difficult. And I think, desired properties, like, of course, we need the sample efficiency, because, all this optimization sub-procedure, this training, for example, in our case, agent training, it requires a lot of quantum queries, which cost. Also, scalability, like to larger qubit systems, right? I don't know. Like, I hope that, for example, the learning-based methods will be able, like because of generalization on some kind of transfer learning, will be able, based on smaller instances of problem, transfer the knowledge to larger systems. But those are only heuristics. But I guess this is the ultimate goal. And then finally, if we want to do the transfer learning, there are open questions. For example, okay, my MDP state is the circuit, but if I want to generalize maybe over the problems, then I have to encode also, for example, information about this operator H, right? Because in the end, right now we are only optimizing, finding the circuit for given only one problem, right? So this is also very, very limited. Yeah, and thank you for attention.
All right. Thanks, Mateusz. And yeah, it's time for questions. Do you have any questions to our speaker? Actually, I can start because I have one. Does the efficiency of this quantum architecture search methods depend somehow of the type of the variation quantum algorithm? I mean, whether it is VQE or QAOA or some variants. Has it been studied? Mm-hmm.
Yeah, to be honest, I'm not sure like the studies explicitly what is the difference, but I can imagine that, for example, VQE, and because of this chemical precision, I guess sometimes we need to be more accurate. Like, for example, there are also people are trying to apply the quantum architecture search into those quantum machine learning. So I guess, then our aim is to obtain, high accuracy, which is probably, 99% is very good accuracy. But in quantum chemistry, we need this chemical accuracy, which requires more careful and more iteration, optimization.
Okay, good. And from the practical point of view, what is the, let's say, maximum depth or the number of gates or the size of the circuit that for which we can apply these techniques nowadays. Is there any because okay.
Yeah, this is hard because I guess the bottleneck is, for example, to train the agent, the bottleneck is the simulation, right? So right now we had experiments on 8-qubit water, but I guess for, I don't know, 20-qubit problem, it will be very hard, right? I guess also it depends on the problem, right? Because sometimes it requires few gates to find even if you have a lot of qubits, we can solve the problem with few gates. But if really to find this particular state, we need a lot of gates, then this is difficult.
And have some of these experiments been run on real physical quantum computers or only on simulators?
I think this quantum darts, or maybe this first quantum architecture search, they have in their paper some experiments on 2-qubit hydrogen problem, some experiments.
All right, good, thank you. Do we have more questions? Yes.
It seems to me that St. Augustine said, "Please, Lord, make me pure, but not yet." So we know, with, as Pavel asked on the if it was started on the real architecture, did you estimate on which level on qubit fidelity it's possible to make this optimization efficient in comparison for example, I don't know, Hartree-Fock method or something like that?
I'm not sure, to be honest. What you were asking, if there was an estimation, like in the literature, how
in literature, or did you
did
you do it or something like that? Because there's big difference, because 97 and 99 qubit fidelity.
Like we yeah, okay. To be honest, right now I'm not sure how what is the answer about the literature. So yeah, I would have
sorry for the question.
First of all, thanks. That was really good thing to see and hear, and very good explanations. I've got one question. It may be done. How many iterations usually we should run when it comes down to reinforced learning? And do we use like a agent site to determine how many iterations during the reinforcement process with those rewards we are going to have?
Like you're asking about the iteration of this internal optimization loop of angles? Or?
Yes.
So, okay, I think we had some experiments, like, for example, okay, of course it depends also on the setup, right? In the noiseless scenario, we ran Kobila with 120 iterations. Yeah, so I guess this is not a lot, but it was also on small instances of problems, right? So yeah, this is like yeah, okay, this is the hyperparameter. Unfortunately, like there is a lot of hyperparameter. Yeah, this is yeah. But this is a good question, and also like you can ask for example, that okay, every time when agent propose the circuit, do we have to optimize it? Maybe we can use some kind of proxy to say if this circuit will pass the chemical accuracy or not. Yeah, so I know that on this year AAAI conference, I think there is some paper about training free methods, and they have some proxies to evaluate the circuits. Yeah, but yeah, this is also like open area, I guess. Yeah, to reduce the number of queries to predict some properties. Yeah, to guess it is good, right? But because maybe it is very, very bad and it is not worth to optimize it. Yeah, but we don't know how to.
Okay, good. Thank you. Thanks for the question. Thanks, Mateusz.
If I understand well, these architecture search methods seem to have bias towards those architectures that are most frequently sampled, but I didn't see any consideration whether those most frequently sampled would actually lead to the optimal solution, right? Because the architecture and the solution is different thing in terms of parameters.
Yeah, of course, but like you have a lot of randomness, right? So like this is kind of exploration problem, yeah.
So you suppose that just randomness is sufficient?
Yeah, but then there's a question: what kind of randomness, right? I don't know. I agree, right? Evolutionary algorithms, for example, you need randomness, and you hope that it will lead you, this exploration phase will lead you to good regions, which is worth to exploit. But in the end, all of those are heuristics, so you have no guarantees, right? Like maybe you could try this, I don't know, annealing methods or something like this, but again, like I think this is not working as good as those. Yeah, so you have no guarantees, right? So then there is the balance. In reinforcement learning, we have this epsilon greedy technique, so that with some probability the action will be drawn from uniform distribution, and kind of it is working right now.
Thanks for the question. Thanks, Mateusz, for the answer. Do we have more questions? So many. Okay.
I was wondering which areas the algorithm would be the most useful in, like for example, like which fields of research. I would say like cryptography or chemistry.
Like there's those quantum
Yeah, yeah.
architecture search.
Or-
Like I guess for now this is the best fit is those variational quantum eigensolvers, like the algorithm. So and the application of those, I understand, is the quantum chemistry. All our experiments are only in the quantum chemistry. I don't know. I believe that this is most promising field. But also those combinatorial optimization. I know that there are also articles with quantum architecture only for this combinatorial optimization. Also, quantum machine learning, as I mentioned. This quantum darts they have in all three domains: the combinatorial optimization, chemistry, and quantum machine learning.
Okay, thank you.
Okay, thank you. Do we have more questions? No more questions. Okay, so let's thank Mateusz once again for a great presentation, answering all the questions. Okay, so now two announcements from my side. So first, I will go back to my slideshow. Yeah, so I hope that you enjoyed this lecture and our Warsaw Quantum Computing Group meetups. You can, of course, follow our groups and profiles and join our mailing lists. And as you know, today we have this World Quantum Day. And one of the organizers of this event is Q Poland, which is one of the so-called Q cousins in the QWORD organization. And there is an idea in QWORD to just prepare just short video recordings with greetings to other Q cousins. So we can just say something like, from Warsaw, happy World Quantum Day, or something like this. So if you are interested and would like to prepare such a recording with us, we can do it just after this talk, and we have great with Mateusz that he can help us prepare it. So we invite you, of course, and we invite you to stay with us for the after party. There is a sushi in the fridge. There are some sandwiches. So hope there will be nice networking. Okay, and that's all from my side. So thanks once again, and yeah, we can finish the official part. Thank you.